Hello and welcome to the Qubit Guy podcast, brought to you by Classiq, the quantum algorithm design company. My name is Yuval, and my guest today is Steve Brierley, CEO and founder of Riverlane. Steve and I talk about quantum error correction, why it's difficult, how soon we can expect it, and much more. We hope you enjoyed this episode. Please let us know how we did by emailing hello@classiq.io. That's hello@classiq.io. Hello, Steve, and thanks for joining me today.
Hi, nice to meet you.
So, who are you and what do you do?
I'm Steve Brierley. I am the CEO and founder of Riverlane, which is a company building the operating system for quantum computing.
So, what does it mean to build an operating system for quantum computing?
Yeah, great question. I think when you think of operating systems, most people would think of a laptop or a PC, and really, what it's all about is managing the complexity for the user. So on your computer, you drag and drop a file. That's really simple, but a whole bunch of complex things happen underneath. And the same is true of quantum computing. Building a useful quantum computer is very complex. There's a lot that needs to happen. And the most complex thing in quantum computing is quantum error correction. And so when I say we're building the operating system, what I mean is we're solving error correction on quantum computers. That's super complex, and none of the users are ever going to see that. We will manage that complexity for the user.
So, your customers are those who are building computers.
So we partner with companies that build computers because, of course, we need qubits as well to make this all work. We help them take the basic components, the individual qubits, and turn them into computers via error correction.
So, if you read the popular press, they say we live in the NISQ area. And so one could believe that there is no error correction going on these days. So, how does it work? I mean, is there error correction? Is there just partial error correction? Where is this heading?
So the big challenge is to implement error correction. Right now, most systems don't have much error correction in them, if any. And so they are limited in how much computation you can perform before the noise starts to kind of take over from the system. So if you think about some of the best quantum computers in the world, say at Google, or the one that is being developed in China at Hefei, these can perform around 100, perhaps maybe even up to like 400 operations before errors or before failure. Like that's amazing. Like that ability to control like individual qubits is astonishing, and it is a really huge breakthrough. But the number of operations we need in order to perform useful computation is way bigger. Like it's on the order of billions of operations. So this gap between kind of computers we have today, the hundreds of operations we can perform, and the billions of operations that we need, that's bridged by error correction, and that's what we're working on.
So, is your code running someplace in a customer computer, or is it primarily under development at the moment?
We're doing a lot of development, and then we're really privileged to be working with lots of different quantum companies and research labs to test out parts of our system. We're not yet at the stage where we have a full-scale system up and running, but we can test bits of it. So we can test components. And I think this is really important because ultimately, a large-scale quantum computer is this hugely complex system. It has literally billions of components and operations, and it's really hard to. And at the end of it, you get some results, right? You get some numbers out, and if it didn't work, then it's really hard to figure out what went wrong. And this is kind of particularly acute in quantum computing. I mean, this is a problem of any large scale system. But in quantum computing, you can't kind of stop the computation and say, oh, hang on a minute, what's happened here, right? So you need ways to build a system up component by component in scale. And so that's why we call ourselves a quantum engineering company, because we're applying these systems engineering techniques in quantum computing. So we're testing components right now, because that's the way to build a large scale system.
And is error correction done by taking some qubits that could have been sort of noisy and putting them to use for the error correction, or is it done in a different way?
Yeah, that's right. Yeah, thanks for the question. So quantum error correction has lots of the same properties as classical error correction, so traditional error correction. So we spread out the information across many quantum bits in order to protect against noise in any one of them. So that's just like classical error correction. So like the simplest error correcting code is, you, instead of sending a 0 or a 1, you send like 000 or 111. And then if any one bit flips, like for example, you receive like 001, you can kind of guess, well, I suppose you meant to send 000. That's a simple code. It's called the repetition code. Quantum codes borrow a lot from classical coding theory, but there's some really interesting twists. And I think the most important one is that quantum error correction happens during the computation. So just to spell this out a bit, because I think it's an important point. So between every operation on the quantum computer, we're going to run this error correction cycle. So we're going to read out some information from the qubits that tells us something about where the errors occurred. We're going to solve a decoding problem. This is a bit like a kind of Sudoku puzzle or something like that. So we're going to solve this decoding puzzle and then react to that. So we're going to change what happens in the future computational steps as a result of this decoding problem. So that error correction cycle, that sort of readout, decode, correct, that's the clock rate of a quantum computer. So that's the like internal clock of the quantum computer, because you have to do that between every quantum operation, between every time you like add two bits together, or every basic operation that's happening in the quantum computer goes around this cycle. So a result of that is that this decoding problem has to happen really quickly, and you're going to have to solve a huge number of decoding problems, like ultimately 10 to the 12, 10 to the 15 decoding problems for every computation that you run. So that's a huge amount of data processing, and that's the big kind of technical engineering challenge that we are addressing at Riverlane.
Is error correction the same regardless of the modality of the qubits? So with superconducting and trapped ions and so on, would they all use the same error correction code?
I think the answer is yes and no. So we absolutely need to adapt how error correction is implemented based on the underlying qubit type. And I would go even further than just superconducting. For example, there are different ways to build superconducting systems, or different types of superconducting qubit, and even different architectures. So qubits connected together in different geometries. So you have to take that into account in your error correcting code. So it's very specialized to the underlying architecture. However, a lot of the machinery and a lot of the problems are the same across the different qubit types. So, for example, the decoding problem, most decoders are essentially solving a particular kind of graph type problem, a matching problem. So that's the kind of core of the commonality across the different qubit types.
Do the characteristics of a qubit in terms of the errors, do they change during the day or, every second? Or is it something that you measure, once a month and then it's pretty much stays the same?
Yeah, also a great question. Yes, they do change over time. Yeah, so you get drift in the system, and we need to take that into account as well. Um, I think over time this does stabilize, and there are multiple processors running um, at various different layers in the stack. But yeah, the temperature changes or the various physical effects are causing drifts in the system, and again that will depend on the particular physical architecture that's being used.
So before error correction is implemented, do you guys provide data that could be used to, for instance, measure the fidelity of qubits in perhaps something that an application could say, oh, qubit 2 is much noisier than qubit 12, and therefore I should assign, the busier operations to qubit 12 instead of 2 or something of that nature?
We don't. Being able to measure and characterize systems is certainly something that is really important. And yeah, I think kind of with if you want to do some demo of a kind of toy problem, then trying to get the most out of the qubits by mapping to certain by trying to take advantage of what's happening is a great thing to do. We're really focused on getting to large scale quantum computing as soon as possible, and so our engineering effort is really on architecting and building the solutions that we need in order to implement large scale error correction. I mean, this decoding problem has never been solved at speed before. Nobody has built it's entirely classical problem. Like it's a classical algorithm that's running, but nobody's been able to solve this fast enough. So the industry has for a long time understood that this would be a problem, and it's really fantastic to be out in a position to be able to solve that.
And forgive my ignorance, but what is it that you sell? Do you sell hardware designs? Do you sell a software algorithm? Do you sell consulting services? What is it that you go to your customers with?
So we partner with hardware companies and allow them to solve to be able to solve error correction. So it's essentially the system that sits on top of the qubits, or that's very close to the qubits, but like in the connects with the control system and runs error correction on top.
So you have a ringside seat to the development of many of the quantum computers. So how close are we to an error corrected computer in your opinion?
Yes, we are. We have a very privileged position because we can we work with lots of different qubit types, different groups ranging from big academic labs to commercial companies. I think the timeline is really one of engineering rather than um, a, a some abstract thing that we're just waiting to happen. So the key things that need to happen are building the classical control electronics and decoding capability that's large enough and fast enough to keep up with the qubits, um, solving some of the material sciences problems in certain different qubit types have different kinds of uh, of physics and engineering type problems. Um, so so from my perspective, is less about time and more about like a list of things that need to get done. And I think what's happening right now is that's that that's been accelerating very rapidly due to the increased investment. So I'm hugely optimistic that we can get there, early um, error corrected systems in the next 4 to 5 years.
Are you worried at all that there's going to be a quantum winter? that the expectations are going to so much exceed reality, then lots of companies will become disillusioned with quantum computers and just put the project off for several years.
I think there's some activity in the space that maybe isn't, will die away, but that's not necessarily a bad thing. I mean, I think what really needs to happen is to solve, like building a quantum computer is a really hard problem, right? I mean, it's like it's not kind of a toy system that we're building. It's something like NASA's like control center, like it's that kind of scale. And so those companies that are addressing that central challenge, there is the appetite there to fund that. And the reason is that the value of what comes out at the end is so huge, right? Quantum computers are not just a bit faster than your CPU. They solve problems that will never otherwise be solved. So there's an exponential computational advantage, right? I mean, and that sounds a bit mathy, but right, what I'm really saying is that there are important problems such as the simulation of quantum physics, which for which classical computers will never be able to solve, and quantum computers will, for the first time, enable us to simulate molecular systems, proteins, catalysis, materials, and that's going to completely transform a whole bunch of industries, like all of those industries that got left behind by the first digital revolution. Like it's the quantum revolution that takes those industries from this kind of discovery phase that they're all in to a design phase where they actually can design products using simulation, just like happens in the aerospace industry. So I think the reason that quantum is going to get funded is because of this huge potential. So yeah, I'm not so worried about the quantum winter. I mean, I think certainly there's a lot of excitement right now. That's actually very helpful. Maybe it's a bit hypey, but like that's attracting good people to come and work on hard problems, and that will result in something very real.
So if you were a master of the quantum universe, and you could control what other companies are doing, is there anything you'd like them to do other than just work faster?
I mean, I think focusing on the core challenges. Um, I think focus. I mean, we focus um, on getting to error corrected systems because it's quantum error correction that makes quantum computers useful. So all of the things that need doing in order to achieve that, like that's the space to work on. Like that's really important. So the more we can understand about, for example, noise in quantum systems, or how to how to control qubits, how to scale them up, things like networked quantum computing as a route to scaling. I mean, I don't think you need to be a master actually, because this is already happening. I think if you look at every qubit type right now, every qubit type has some big science challenge. Like there's something really big that needs solving in order for that to become the transistor of quantum computing. Right? That it doesn't matter if you're superconducting, ion trap physics. There's something within each of those that is a big hairy challenge. And I think the great thing is that for all of these challenges, there are companies that have got brilliant ideas for how to solve these. And that's happening right across the different physics approaches. Um,
So as we get closer to the end of our conversation, I think that you've been working on this for 15 years. So, I gather that you like it, but why is it taking so long? Is it just a terribly difficult problem? Is it that funding was not available early enough? Not many problems take 15 years to solve.
yeah, so I've been working on quantum computing for 15 years. I mean, I started working on quantum algorithms. Um, So this is what would you do with a quantum computer once one was built, right? And this is very theoretical. I worked in academia at Bristol University and then here in Cambridge. And actually, I founded Riverlane because of a moment at a conference. So I was giving a talk about a recent algorithm that I developed, and at this conference there was this straw poll of like who thought there would be a quantum computer in the next 5, 10, 15 years, and so on. And about a third of the audience, so this was all like the kind of great and the good of quantum algorithms and quite a few physicists, a third of the audience voted that there would never be a useful quantum computer. I was just really shocked, and at, I guess partly the pessimism. I mean, I guess it's like academic space is like people are pretty pessimistic, but maybe I was working on developing algorithms for a computer that would never be built. And so I went back and started to talk to the experimentalists, talk to people building qubits. This was about 5 years ago, and they had at that point 10, 15 years of data of like how good are you at building the basic, how good are you building a qubit, like in photonics. So Jeremy O'Brien at the time was at Bristol, so he was asking his group. So now PsiQuantum, is it talking to the ion trap folks over at Oxford and the superconducting people, and what I saw was this trend that like we were getting closer to solving the underlying physics of controlling individual quantum computers. And so what was needed was to make this useful. Like what was really missing was the engineering approach to scaling up quantum computers. You've got lots of great physics labs around the world getting a handle and control on individual qubits, and now is the time to bring people from other fields to solve the engineering challenge. So that was 5 years ago at Riverlane, and we are now motoring ahead on solving that.
So, Steve, fingers crossed for your rapid success. And how can people get in touch with you to learn more about your work?
So email me, steve.brierley@riverlane.com, or we have a website. That's a great jumping off point. For example, we have a newsletter, so that's riverlane.com. Yeah, or reach me on LinkedIn. Yeah, happy to answer any questions.
Excellent. Well, thank you so much for joining me today.
Great, thank you. I enjoyed the chat.